Welcome all. The MfPH Next Generation Seminar Series is a networking event for early career scholars, junior modelers, and epidemiologists working on or interested in mathematical modeling of infectious diseases and other threats to public health. Bienvenue à tous. La série de séminaires MfPH Next Generation est un événement pour les chercheurs en début de carrière, modélisateurs juniors et les épidémiologistes travaillant intéressés par la modélisation mathématique des maladies infectieuses et d'autres menaces pour la santé publique. First of all, we wish to acknowledge this land on which the Fields Institute operates for thousands of years. It has been the traditional land of Huron-Wendat, Seneca, and Mississaugas of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Premièrement, nous souhaitons reconnaître cette terre sur laquelle l'Institut Fields opère depuis des milliers d'années. C'est la terre traditionnelle des Huron-Wendat, des Sénèques, Mississaugas. Aujourd'hui, ce lieu de rencontre abrite encore de nombreux peuples autochtones de toute Turtle Island et nous sommes reconnaissants d'avoir l'opportunité de travailler sur cette terre. Our guest today, Arvin Vaziry from Dalhousie University, is a PhD student working on application of partial differential equations in mathematical biology. He holds a master's degree in applied mathematics from Dalhousie University, where he started investigating infectious disease models and derived a novel spatiotemporal PDE. And he got his bachelor from Khaja Nasser Tousi University of Technology in Iran. Notre invité aujourd'hui, Arvin Vaziry, est de l'Université Dalhousie, est un doctorant qui travaille sur l'application des équations aux dérivées partielles en biologie. Il est titulaire d'une maîtrise en mathématiques appliquées de l'Université Dalhousie, où il a commencé à étudier les modèles mathématiques de maladies infectieuses, à dériver une nouvelle EDP spatio-temporelle en ce sujet. Il a obtenu son bachelor à l'Université Technologie Khaja Nasser Tousi en Iran. His talk will be on modeling of spatial infection spread through heterogeneous population from lattice to partial differential equation models. Sa présentation portera sur modélisation de la propagation spatiale de l'infection à travers une population hétérogène, des modèles de réseau aux modèles d'équation aux dérivés partielles. Thank you very much for accepting our invitation, and the floor is yours.
Thank you very much, Idris. Hello, everybody. I hope you are all doing very well. It's my honor to be here and present our work on mathematical modeling of infectious spread. It's been a joint work with my supervisor, Theodore Kolkolnikov, and Panos Kavakidis from University of Massachusetts. Okay, let's get started with a little bit of introduction. Our focus in this research has been on spatially distributed models, exploring the evolution of infections, not only temporally, but spatially. We were trying to incorporate the spatial term and kind of understand the role and effect of people's motion and travels in the spread of COVID. So we start by a nonlinear dynamical lattice-based approach, and we drive the continuum limit to obtain a novel PDE model. Okay, at the heart of many epidemiology model is so-called compartmental models, and in the frame of our study, we use that. But the main idea is to divide population into different blocks and study the flow of population from one to the other. The flow of people are governed by the set of ODs. And here you see a compartmental model consisting of different departments from susceptibles, exposed, asymptotic, and asymptomatic, and in recovered, hospital, and many other compartments. But in the frame of our study, because we want to propose an idea of the role of people's motion on the spread of COVID, we are going to choose and stick to the most simple SIR compartmental model, which is SIR model. This is a set of equation ODs that govern this the flow of population. We have the S represents susceptibles, I represent infected, and R represent recovered cases. Here I should correct this. This is actually dr dt, which is gamma. We have some constant here, is beta and gamma, which shows the interaction between susceptible and infected, and also the rate of recovery of people. Okay, I think I can continue. Okay, this equation admits a very trivial equilibrium, which is at the beginning. When we don't have any infected cases, then there's no outbreak. Okay, first of all, let's say that the very beginning of outbreak, we can say that S is almost the same as initial population distribution, is like S naught. And then we can write di dt to be like this. Okay, when we have outbreak, that means di dt is positive, di dt positive, which in terms means that beta is not, this part should be positive, or beta is not over gamma should be greater than 1. So this is this ratio is called basic reproduction number, which you might heard a lot about during this COVID and during this outbreak. Okay, so there, our study was triggered with 2 observations. One is all the epidemic or all the outbreak was captured with a single number, which was just a single number, simple single number that diagnosed the epidemic through all the country, all the region that we have, for example, for a country. Okay, but we know that R naught is just a number. It can change locally. It doesn't have any spatial term in it. For example, it's obvious that in an urban area that we have more population, we expect to have more infected cases. But there is no spatial term in this basic reproduction number. The other thing is, when you review the literature, you will find a lot of studies and papers that introduce the affect the population motion and diffusion by adding these terms to our previous set of ODs. What are these? But let's have a closer look on these terms. Okay. So we have a diffusion term like SXX, but what is the story of that? The story of this diffusion is just the random movement of people, this Brownian motion. What does it say is, when we have a heterogeneous distribution of population like this, it moves to, it levels off after a while, and everywhere had the same population. But is it the story behind the people's motion? We think it's not the case. It's not the case. People don't move randomly. There's very certain rules. People, for example, go to grocery store, buy something, and then return to their home. They go to work and then return to home. So this is not a random walk, or this is not. This is very naive approach to incorporate the spatial term just by adding some terms like the diffusion term and the second derivative with respect to position into this set of ODs. Okay, what we think is happening is here. Okay, first of all, let's divide our population into different bins, like n bins, okay? And say, let's consider just the grid point J. Let's assume just susceptible will travel at this time. So we have some susceptible at grid point J. They part of this population will travel to adjacent grid points J minus 1 and J plus 1. Okay, susceptibles that will travel to this grid point will be have interaction with infected cases here. So that means we have some new cases because of interaction of people, susceptible peoples who travel to adjacent points. Okay, so how we are going to capture these terms? Okay, so this is this is what we propose. We say, first of all, the population here is like Sj. Okay, so then Sj. Let me highlight this part. Okay, So alpha Sj of this population at point J will travel to J minus 1, and they have interaction with infected cases at that point. And with rate of beta, they will turn to the compartment of infected cases. Okay, same thing will happen for the beam J plus 1. We have, let's say, the same rate of people will travel to J plus 1. So then we have new cases that is because of interaction between susceptible and infected of J plus 1. Okay, susceptible who are stayed in this beam J will have interaction with Ij, but 2 alpha Sj is already traveled to adjacent point. What is left is S minus 2 alpha Sj. So, so this is the discretized model that we see. First of all, it described the story in this way. And now let's consider the continuum limit.
Arvin, excuse me, may I interrupt you? Sorry.
Yeah.
So in the previous slide,
Sure.
so you have two steps of the time, right? So T1 and T2. So what is the middle? So why you have not considered that one as a T2? Because I was thinking the first arrow should be T1, the second one T2, and the third one T3.
Oh, right.
I understand the middle part, right?
Right. Very good question. Actually, you see, it's the time between, for example, let's say we are talking about the time interval of within a day, okay? So
Right.
within a day, we expect that people will travel, for example, to the work, right? Let's say J minus 1, J minus 1 and J plus 1 are two places for work, okay? People go to these places, and at the end of the day, they will return to their home point, which is
okay.
yeah, it's just showing what is happening during this interval time, like delta t or something like that.
Right, I got it.
Okay, thanks for the question. Yeah, please feel free to interrupt me. I'd like to have interactive presentation. Okay, should I continue? Do we have any other questions? Okay. So let's.
Sorry, Arvin.
Sure.
I just put a question on the chat box. I was asking, wouldn't you have a recovery term in the formula 4? Because that's the variation of the infectives in the block
Right.
G.
Right. But yeah. We very good question. We consider that. Okay, we consider that, and we say that we talk. It's okay. Let's go back here. It's minus gamma I, right? And it's part. We first find what is happening. How many infected cases we have at the end of the day. Then we consider that in our equation, in our setup. You will see later, okay? We just want to see how many infected cases we will have by this interaction between people. Does that answer your question? Okay. So let's rewrite.
Sorry to interrupt. Maybe if we leave all the questions at the end of your talk, so we can you can present all the talk, and after that you can answer the questions.
Okay. So sorry. Let's rewrite the terms, and in this way, I just bring the terms like I factor out Sj at time t. That is, we have. Okay, let's put it this way: the new cases of that happening because of this travel, this alpha ray, this travel to the adjacent point. I put it, gather all of them this way. So, and if you notice here, it's just the discretized second derivative of I, spatially. So let's introduce, let's assume that we have discretized I into different bins, and IXT becomes IJT, where X is actually J delta X, okay? And like increment steps. And hence we so because of that is just like the second derivative, the spatial derivative of I. Okay, let's see how does it change our story, how the equations. Okay, in the limit when delta x and delta t tends to 0, and by disregarding higher orders of delta x, we can rewrite the equation in this way. The delta I, the new infected cases, is going to be beta si plus delta x squared alpha si xx. Okay, let's do something else as well. Next step, let's define this variable here to be our diffusion rate, alpha delta x squared, and then we can write delta I to be beta si plus dsi xx. Okay, so so we figured out what is the new cases. Okay, these new cases will be subtracted from susceptibles, will be added to infected cases. So it appears with negative sign for ST. It appears at with positive sign for infected cases, and this is the setup of our equation. One thing I want to highlight here is, unlike previous models that you see in the literatures and other papers, here the diffusion term appears with negative sign for susceptibles, actually with negative sign here, and with positive sign for infected cases. And let me go back quickly to the, okay, sorry, shouldn't do that. Okay, maybe my tablet is not happy with what I wanted to do. Okay, so yeah, previously, let me write it here. Previously, we had ST like beta SI plus DSX, for example. IT was something like beta SI plus DIXX. But look at here. We have S term here, and also this sign is very important, right? So so let's go to next slide. Okay. So yeah, as I explained, the diffusion term happening is show up with different sign for susceptibles and infected cases, and actually it's not just some number like some diffusion term times the spatial differentiation. Okay, it was a special case that we studied, that we assumed that only susceptibles can travel. But what happens if we have infected cases can also travel? In that case, people who travel to adjacent points, okay, people who travel to adjacent point, let me go back to my diagram here. Okay, then people who travel from, for example, J to J-1, they might have interaction with infected cases who travels from J-2. Then we expect to have more new cases in this case. Okay, so let's see how does that change the equations. We expect to have this extra terms, right? So let's assume that people's travel, this infected cases will travel with alpha I, and the susceptible will travel with alpha S, let's say different rates. This is the general discretized model. And when we take the continuum limit, we can get to this equation again. Same approach. We can derive this equation, and then we can introduce two different diffusion rates, like ds for the diffusion of susceptibles and diffusion of infected cases, to define it like this. And also by assuming that they have, we can introduce a general d as ds plus di, and change the setup of equation to make a generalized equation for the for this case and for this scenario. So that's basically our main idea about how this how we can capture the motion of people inside the equation instead of just throwing some spatial term into our equations. Okay, now let's study this equation and see how the result might look like. First of all, introducing infected cases to a set of population distribution may cause a wave across this across the domain. So in order to study this wave, let's focus on the front of the wave when we have very few infected cases. In that case, we might use some KPV and some analysis to find the speed of propagation of this wave. Okay, at the very front of outbreak wave, we might have very negligible recovered cases. Okay, so in that case, we can say that RSXT actually is just initial population distribution and minus some infected cases that is happening, is happened, right? We have at the very beginning. Okay, so then by plugging this result into our main equation that we derived in previous chapter, we can get to this equation. Okay, next step, let's disregard higher order terms of I because we have very few infected cases. Then we get to this equation, which is very similar to KPP equation. And we can use the same idea to linearize the very front of our outbreak wave. Okay, so let's again, motion is sufficiently slow, and also the diffusion is very, very small. Then we can linearize I with this exponential function e to the lambda x minus ct. Okay, plugging this into our main equation, then solving this for c, we can capture this equation. By doing some simplification, we can capture this equation for c. C is in terms of lambda. Okay, so we are interested in finding the minimum speed of propagation. Okay, so let's take derivative of this function with respect to lambda and find the optimum points. By solving the equation, we get two lambda, positive and negative, which by considering the right way of the propagation, right direction of propagation, we can find the minimum speed of this wave. Which is to be 2 square root of beta is not minus gamma, beta is not nd. Okay, let's see how this asymptotic analysis is doing well. Okay, here is the result. We run the full numerical solution of this set of equation and compare it with our asymptotic solution. As you see, the first case it shows well agreement between asymptotic solution and full numerical solution. In the first case, we used the initial population distribution to be 1 plus 0.4 times sine 4 pi x. But for the second one, as you see, the error increased for this part. And you might guess that it's because it changed faster. We have the derivative of population and initial population is more than previous one. So this, so yeah, it's the function is 1 plus 0.7 sine 4 pi x. So it means that as we have more population and its speed, the wave propagates faster. In our asymptotic solution might have errors. But in the case that we have more smooth population distribution, it shows really promising results. Okay, and it's a well-known property of speed of propagation for KPP equation that we say that the speed of propagation approaches this minimum velocity or the minimum c with the range of initial condition as long as this the R domain or our main function decays sufficiently fast as we approaches to the endpoints of our interval. Okay, by the way, let's move on. After studying this wave and finding the speed of this propagation, let's talk about onset of outbreak. Okay. So at the beginning, I mentioned that in previous study, they throw just some spatial terms. And the other thing was they captured the outbreak with a simple single numbers variable like gamma, basic reproduction number, to say that to determine if you have outbreak or not, to be the threshold of outbreak. But let's see how we can incorporate this spatial term to find a better measurement for the outbreak, for the threshold of outbreak. Okay, so the main equation admits a trivial solution when we have no infected cases. Okay, obviously we don't have outbreak. Okay, then we have Sx to be the same as our initial population distribution. Okay, so then on the other side of the outbreak, we assume that the infected cases are very small. Then we have the approximate solution for IT to be something like that. And in that case, we can linearize I to be the something like this. Okay, let me write it here. Okay, we say I, x and t to be I at the equilibrium point, which is 0 plus E lambda t phi x. Okay, I is 0, so this is how we are going to linearize when we are about the outbreak. I mean when we want to linearize around the equilibrium point. Okay, so we will obtain this eigenvalue problem. So next step, we want to find this threshold within two regimes. The first regime is when the fusion rate is very small and the leading order would be 0. Okay, let's say D is 0. Then lambda becomes this by solving that equation. By solving the equation, we obtain this equation for lambda of this eigenvalue. Okay, then what is the threshold? The threshold or critical value is going to be when gamma is less than beta, is greater than beta S naught, and the threshold is going when gamma equals beta S naught. But because we want to find the critical value, we should consider S naught depends on X, okay? So the critical value is going to be the beta times max of this population distribution over the domain, okay? So, but this is the leading order, right? When we say that, okay, let's say the D is 0, this is going to be the leading term, or it's going to be depends on the max of S. But what is the correction of this critical value? In order to find that, let's rewrite the equation, and let's assume that D is something between 0 and 1 is way less than 1 as order of epsilon or something like that. And using asymptotic analysis, we are going to derive the critical value. Okay, so let's zoom in around XM. Let's say that our maximum of S naught is going to happen inside the boundary. Okay, let's say, for example, this is our boundary from 0 to L, and the max is happening somewhere here. It's XM. So let's zoom in this region. Okay, how we are going to do that? We introduce our new variable y. We say we are going to expand. We are going to say that x equals xm plus epsilon. Well, it helps us to zoom into that region. Okay, plugging that into our eigenvalue problem, we are going to obtain the very well-known equation, which is quantum harmonic oscillator. This equation is this eigenfunction is given based on Hermite polynomial, and it's okay. I should write it here. Okay, it's eigenfunctions here for this equation. Eigenfunctions are in terms of Hermite polynomial, and the eigenvalues are the eigenvalues of this equation. Eigenvalue problem is going to be something 1, 3, 5, 7, and so on. Okay, but we are interested in finding the critical value, right? So we should consider the smallest eigenvalue, which is mu to be 1. By plugging that into the equation, we obtain this this formula for threshold of gamma. Okay, so this is the correction. Let's do an example. Let's run as numerics and see how the results are doing asymptotic and comparing asymptotic and numerical result. So as you see, the difference between the relative error is less than 1%, and as we decrease the to 0.00125, the error is goes down by almost 0.1%, which is really promising for this approximation. Okay, so first we assume that the maximum is happening inside the boundary. Okay, but what happens if we consider it happens on the boundary? Like, let's say we have, again, let's from 0 to L, and then we have, this is our boundary, and we have some function like this. Okay, if you want to write the polynomial arterial expansion around this point, which is, for example, 0, then we have, we can just work on the first order, right? The first degree of x minus xm. Okay, so let's do that. Let's write S naught to be something like that for some constant A, B to be found based on the population distribution at point A and its derivative at point, xm, which is the max of x. And by plugging the results into the eigenvalue function, eigenvalue equation that we have, eigenvalue problem that we have, we obtain this equation. This is also a well-known equation. We just rewrite the terms, we define new variable, change a variable, we can get to the Airy equation. So the Airy equation, the solution to Airy equation is Airy and Bailey function. Okay, how we are going to find this constant? By considering the boundary condition that we have for this problem. First of all, this is no flux problem. I mean, we have Neumann boundary condition, right? The first derivative at the endpoint should be right and left endpoint should be 0. And by considering that the limit as our domain as as y tends to infinity, it should be, the derivative should be 0 because we expect that people don't blow up. So because of that, so the constant for Bailey function should be 0. And following that by and also we know that the derivative at the boundary should be 0. So by plugging the results and plugging the results into the equation that we have, we can obtain the minimum value by considering the first point to satisfy this equation, because basically Airy function is the Airy function is oscillating this way. So by considering that something like that, by considering the first point, we are going to obtain our critical value for gamma, which is going to be something like the ratio of the gamma 1 over b should be negative 1.0188. Okay, the threshold then can be obtained by using this formula, and by doing further simplification and applying a numerical solution, you can see the comparison between the numerical and asymptotic results. So it's again shows a very good agreement with full numerical solution with around 0.08% error, relative error for the case of d equals 0.00125. Okay. And that was a story when d is very small, but what happens when d is very large, like of order, I don't know, like maybe we can think of 1 in this case, okay? So the leading order of our solution for eigenfunction is going to be constant by plugging into result. Basically, we are going to expand in our asymptotic solution, we are going to expand phi to be something like phi naught plus 1 over d phi 1 and so on, okay? By plugging this expansion into the equation, we first of all, we know that the leading order is going to be some constant. And the next order eigenvalue problem is going to be something like this. And by solving, integrating both sides on the domain, we can obtain the critical value. And it's very interesting that inside this critical value, we have the harmonic average. It's well now this 1 over L. Sorry, I should use. Okay, this part is harmonic average of the harmonic average of the population over the interval, over the domain. So the critical value of gamma is going to be, depends on this harmonic average. So, okay, let's again do the case, this numerical case. It shows it perfectly follows, and you see asymptotic solution perfectly follows the numerics, and we have about 0.1% of error. Okay, let's put all these results together for small diffusion and large diffusion. Plot it into semi-logarithmic plot, and you see that for a small value, it's okay. So this is the large. This blue line shows the large d asymptotic. This dash green red line shows the small asymptotic. It shows very good results, good agreement in this region. When d is very small and when d is very large, in between we have error. And we kind of find the bounds of this function, which for the critical value of gamma. Okay. So that was our, okay, we find a better way of representing basic reproduction number for finding the outbreak, the threshold of outbreak. But let's have a look at data. Although this motivation was, this project was done during COVID, but we didn't do a lot of data. We basically focus on the analytic solution and doing analysis on the formula, but we could qualitatively regenerate part of our observation in Nova Scotia. In Nova Scotia, let me provide you with a little bit of background, demographic and population background. So we has a population, Nova Scotia has a population of 1 million. Half of them are living in Halifax, and half of them is live in Sydney, which is the second biggest in Nova Scotia. The distance between these two cities is about 400 kilometers or 4.5 hours drive. Generally, we did very good during COVID in Nova Scotia. In total, we had about 5,800 cases, which is around 0.6% of the total population. We didn't have really outbreak there, but except just for a while that I'm going to explain in July, we had outbreak. In the most infected cases reached about, I think, 50 people. So the interesting observation was, although 90% of the all population, all the infected cases will live in Halifax and Sydney, and okay, despite this relatively a smaller size of infectious rate in Sydney, the outbreak happens 2.5 times the infectious rate that happens in Halifax, and it was quite interesting. Okay, we run a simulation code using our equations, our novel PDE model, to see how we can kind of make sense of this observation. Okay, we run. Firstly, we define this initial population distribution to be something like this red curve at the beginning. Okay. this can represent two cities that has a buffer zone in between. Like we can think of this region like Sydney, this part like Halifax. Okay, and in between there is a between these two cities we have a rural area like or like a buffer zone. Okay, so what we did is we introduced very few infected cases, at the very left endpoint of this domain here. We introduced very few infected cases at this point, and then we run the simulation and see what happens. Okay, it was very interesting that this outbreak suppressed inside this region after a time interval like from 0 to 20 or 40, and for a while we didn't see anything. From time 40 to 100, there was nothing significant happening in those regions. But suddenly, at time 100, this outbreak finds its way to the second city or second region and hits the max of the population in the second region. And then it propagates an outbreak, and after a while it's suppressed. Okay, and here is the plot of the infected cases. And here's the point that we introduced in few infected cases. As you see, dies out this outbreak. Nothing happened for a while, and up to this point that we see an outbreak in the second region, and it first hit the max of this population, and the maximum, the point that the population was max, and then spread out through this region. So, okay, that was one observation that we could regenerate qualitatively using our model. But I want to talk a little bit about a model that it doesn't mean there is no physical meaning for this regime that we consider for this part, but it just, from mathematical point of view, it was interesting. We first expand S and I. We consider D to be very large, okay, even larger than 1, okay? And then we expand S and I in terms of 1 over S naught to be, S to be S naught plus 1 over DS1 and so on, okay? And then plug everything into the equation, and we obtain something like this, okay? The leading order of this equation has a solution like Ixx to be 0, okay? So that considering Neumann boundary condition, based on this result, we can conclude that I naught won't change in space, and it only depends on time. So then we run a simulation, and we observe very interesting that this initial population S basically reduced like an OD. It wasn't changed spatially. It just, each point has kind of comes down. We like drag this function down up to here, and this infected cases grows samely everywhere. Okay, so how we can make sense of this result? Okay, again, we expand S, we rewrite S naught to be initial population with some function of time, and then we plug in into the equation to find the next orders. Because I think I should be a bit faster, I guess. So by writing the equation and plugging the results into the equation, and we obtain this result here, okay? And which in turns, I want to show you the final result. Yeah, here. Okay. We drive the equation. Basically, if you remember, we defined S to be S naught plus some function of time, okay? And then which S naught is basically the initial population, it depends on X, and after that you have just some function. It doesn't, and the rate of change, basically the change of S was happening not spatially, just with time, okay? Okay, so and this is the derivative of ft, and the original PD equation reduced to a set of ODE, and we try to obtain the numerical discretization of this main equation with d equals 1, and do this analytic using this initial population of to be the format of sine, and here's the result of our result. Okay, but as I mentioned, this doesn't mean anything in physical reality, because we need to be very large is like people can have interaction with everywhere, with everyone. Is a lot of interaction, and this was our result. So lots of question is we are considering for our further research, especially about the part of the buffer zones. We are interested in finding the speed of propagation in buffer zones, how the outbreak transfer from one region to the other one. And also we like to have demographic data and including these more compartments into this equation. I think that's it, and I can stop here and take your questions.
Thank you very much. Is there any